All right, morning everybody. Today's topic here, we're going to talk about thermodynamics. Thermodynamics literally means heat changing. All right, so heat is changing, of course, with respect to time. Now, we're going to talk about the first two laws. There's actually two other laws. If you want to do a little bit more, research on your own about that. So, first of all, the first law of thermodynamics. It states that the change in thermal energy of an object is equal to the heat added minus the work done by the object. All right, so in other words, there's a formula here. The change in thermal energy is denoted by delta U. The heat added to the system is denoted by the letter Q, and the work done by the object or system is denoted by the letter W. So you have this formula called delta U equals Q minus W. I'll show you how to solve that here momentarily. Now, this law, the first law of thermodynamics, it is merely a restatement of the law of conservation of energy, which we haven't talked about. But the law of conservation of energy basically just states that energy can neither be created nor destroyed. All right, it is only transformed. It can be changed from one form to another. So really, to be more scientifically accurate, from this point forward, you should never say to anyone or to yourself, I have no energy, because you do have energy. You wake up in the morning, maybe you're tired, maybe you're a little bit sluggish, you still have energy. All right, your body temperature still is around 98.6 degrees Fahrenheit, 37 degrees Celsius, or to 300 Kelvin. No, 310 Kelvin, sorry, 310 Kelvin. Anyway, but you still have energy. It may not be in its usable form, but by having something to eat, something healthy, cereal, banana, eggs, whatever, that food will provide you energy so you can function, in your daily life. Now, this, so again, energy can neither be created nor destroyed. It is only transformed. All right, that's basically the first law of thermodynamics. There is the equation that goes with it, and I'm going to show you how to solve these equations, and it's really not that bad at all. All right, as you can see, you're just subtracting one number from another. We're talking about the quantity of heat added to the system minus the work that is done by the system. So, for example, you might have a problem like this. Let's say that the energy the system is gaining 1,500 joules of energy, and the work done by the system is 2,200 joules. All right, so you simply subtract the two. Yes, you're going to have a negative number here. 1,500 minus 2,200 is negative 700 joules. So when we're working with this particular formula, you'll see it on the worksheet called Thermodynamics. It's called Thermodynamics on the file, but it's actually called First Law of Thermodynamics, Second Law of Thermodynamics. But anyway, when you're working with this equation here, your answer will always be negative, okay? It'll always be a negative number. And to make it easy, I have nice round even numbers like this, 1,500 minus 2,200, so on and so forth. You'll see what I mean when you take a look at that worksheet. So that's basically the first law of thermodynamics. Okay. Again, we're saying that energy can neither be created nor destroyed. It can merely be transformed in a system. And again, you can also think about the change in thermal energy is equal to the heat added minus the work added to the system minus the work done by the system. So also on the same worksheet, you will see problems involving the second law of thermodynamics. And the second law of thermodynamics, basically it states that entropy increases with time. So you might be saying to yourself, well, let me back this up a little bit. What is entropy? All right, what is entropy? Well, entropy, there's two definitions of it. First definition, it's a measure of energy dispersal in a system. So like I was just showing you with that delta U equals Q minus W, right here, So what we're talking about, what we have here is like if you have this system, all right, put your hands together like this. If this is a system, then the energy, the entropy is looking at, all right, where is this energy, how is this energy being dispersed in the system? Well, according to this, because it's a negative number, the energy is leaving the system and going out into the environment. So for example, if you're in a cold environment, you still have a body temperature of 98.6 degrees Fahrenheit, 37 degrees Celsius. But if you're in a cold environment, like, let's say a couple months ago, it was winter, and well, shoot, we had winter. It seemed like just the other day, last week I think it was, but anyway, it's a cold environment. So if you're not dressed appropriately to go outside on a cold day, you're going to get cold. Your body temperature is going to drop, all right? And of course, your nervous system and all that's going to fight that, and so on and so forth. That's a lesson for another day. But what we're talking about here is the heat from your body is being dispersed into the environment. All right? That's one definition of entropy. Okay? Measure of energy dispersal in a system. All right? So like I just talked about. This another definition of entropy, the measure of disorder in a system. Okay? I have here a deck of cards. All right? It's been shuffled, but whatever, it's not in any particular order. I have no idea what order it's in. But if you notice here, we have a nice neat stack of these cards. Well, we could do this, and the cards are basically flying all over the place, and now I'm throwing them at the camera there. Now I have entropy. Okay? Just to show you here on the floor, I don't know if you can see that, besides the wonderful glare from the window, but there's a bunch of cards on the floor. So that's basically demonstrating entropy. Now, some of you, if you have a messy bedroom at home, and you know who you are, but if this is you, then you're demonstrating a scientific law. You're demonstrating the concept of entropy. Now, whether you use that as your defense with your parent or guardian, saying, hey, go clean up your room, I don't know if you should use that or not. You know your parent or guardian best. So anyway, what we have here, a measure of disorder in the system. I showed you the disorder. I threw that, the deck of cards, it's all over the floor now. And if I slip and fall, don't laugh. Now, we have an equation, or formula rather, to help you calculate the change in entropy. All right, we have delta S, change in entropy, equals Q. Oh, good grief, look at these arrows here. I see like 4 of them right here. What's going on? All right, so you might recall this formula here. Q equals M times H sub F. Okay, the heat of fusion, which, you completed that assignment ideally before 11:59 last night. Well, Q equals M times H sub F. Well, what we do is we take that and we plug it in for Q here, and we divide it by T. Now, so what we're going to take mass times heat of fusion, and we're going to divide that by the temperature. The temperature is in Kelvin. All right, guess what? I don't give you the temperature in Kelvin. You have to convert it to Kelvin. Please show me that work. It's a simple step. Some of you thinking, I don't need to do that. Yeah, you need to do that. So make sure you show your work. Okay, so typically speaking, we're talking about a change in entropy when a block of ice melts. Okay, so we might have, let's say the block of ice has a mass of, let's say 8 kilograms. All right, so here's your example for using this equation here. The heat of fusion of water I'm going to give you is 3.34 times 10 to the 5th joules per kilogram. All right, so this is your mass, this is your heat of fusion. We're going to divide that by the temperature. By the way, the temperature will be provided at 1 degree Celsius. Do not take this here and divide it by 1. Let's turn this a little bit. Yeah, there we go. Okay, don't take this and divide it by 1. You're going to get some gigantic number. It's about this big. All right, we don't want that. We want you to make sure that you convert the temperature to Kelvin. So how do you do that? 1 degree Celsius plus 273 equals 274, right? Hopefully you didn't need a calculator for that, but hey, more power to you. All right, now, what you do then, I'm not going to like count it wrong if you don't cancel out units, but I'm just going to show you, just for the sake of showing you. Kilograms is here and here. I can get rid of those, and then I can just multiply across 8 times 3.34 times 10 to the 5th and divide by 274. If you don't know that off the top of your head, then I suggest you get out your handy-dandy calculator and you figure this out. Newsflash, I don't know this off the top of my head, so here's my handy-dandy calculator. So we're going to do 8 times 3.34 times 10 exponent 5, then equals, then we're going to divide that by 274. Again, if you don't divide by 274, or if you just divide it by 1, you're going to get a really large number, but really the answer you're looking for here is 9,751.82 or so joules per Kelvin. Whoops. Joules per Kelvin. All right, written as J/K. Not like just kidding. It's just joules per Kelvin. All right. So that's how you handle calculating change in entropy. Okay. You just use this equation here. Let me get to this side. All right. Delta S equals Q over T. Again, Q is M times H sub F. I define, M is mass, H sub F is heat of fusion. We're talking about something melting. We're not vaporizing anything. We're just melting it. And then the temperature, of course, is in Kelvin, so make sure you convert to Kelvin like I did here, and you get that as an answer. So that was the first and second laws of thermodynamics. Again, first law basically is saying that the change in thermal energy is equal to the energy going in minus the work that's being done on the system or by the system. Excuse me. Another way of saying that, again, is energy can neither be created nor destroyed. Second law of thermodynamics, on the other hand, energy dispersal in the system, it's a measure of entropy. It looks at entropy, all right? Entropy increases with time, all right? Believe it or not, as we age, entropy is increasing in our own bodies, all right? And basically, that's the way it is. So, give this worksheet a shot. Again, it's called Thermodynamics. There's like a total of 8 questions. The ones that don't involve the problems directly, you're free to, if you borrowed a physics book, you can look up those answers that are in chapter 12. I know many of you will just end up Googling the question or something to that effect, and that's fine too. But just make sure you're following directions, because I do want you to show your work, and I do ask that you use complete sentences when answering short answer questions. So, with that, that's all I really have to say with regards to this. So if you have questions, let me know, and we'll go from there, and let's buckle down, take care of business, because I don't know about you, but the light at the end of that tunnel is starting to get a little bit brighter at this point. So take care of business.